Good morning, everyone. I'm Professor Rahul Chowdhury, and welcome to our comprehensive course on memory management. Today, we're diving deep into one of the most fundamental aspects of systems programming that every computer science professional needs to master. Memory management sits at the heart of efficient system programming. It's not just an academic concept. It's the foundation that determines whether your programs run smoothly or crash spectacularly in real-world applications. Let's start with why this is critically important. Memory management directly impacts program execution efficiency, determines how well your applications scale, and affects overall system stability. Poor memory management leads to memory leaks, crashes, and frustrated users. Throughout this course, we'll explore core concepts that form the backbone of memory management. We'll distinguish between physical and virtual memory, examine different allocation strategies, and understand how modern operating systems orchestrate these complex operations behind the scenes. The real-world impact cannot be overstated. Mastering these concepts will enable you to write programs that achieve significant performance gains, maintain system reliability under load, and efficiently utilize hardware resources skills that are invaluable in today's computing landscape. By understanding memory management principles, you'll be equipped to optimize applications, debug complex memory issues, and design systems that scale effectively. This knowledge will serve as your foundation as we progress through the practical demonstrations and assessments ahead. Building on our introduction to memory management fundamentals, let's now dive deep into the anatomy of memory itself. Today, we're exploring the anatomy of memory, understanding how computer memory is structured and organized at its core. First, let's examine the memory hierarchy. Think of this as a pyramid. At the top, we have registers, the fastest but smallest memory. Then cache memory, followed by RAM, and finally storage devices like hard drives at the bottom. Each level trades speed for capacity. Next, we need to understand memory allocation, specifically the difference between stack and heap management. The stack is like a neat pile of plates, last in, first out. The heap is more like a parking lot where you can park anywhere there's space. Memory addressing is crucial. Every piece of data needs an address so the CPU can find it. Think of it like a postal system where every house has a unique address within an address space. Finally, the physical layout involves memory segments, different sections of memory reserved for different purposes like code, data, and system information. These four components work together to create an efficient memory system. Understanding this anatomy is essential before we move on to visualizing how memory access actually works in practice. Now that we've visualized how memory access works, let's dive deeper into the actual mechanisms of reading and writing from memory. This is where we'll explore the fundamental operations that make data transfer between CPU and memory possible. First, let's examine load and store instructions. These are the core operations for CPU memory data transfer. Load instructions bring data from memory into CPU registers, while store instructions write data from registers back to memory locations. Memory access cycles determine the timing and performance of these operations. Each memory access follows a specific sequence: address setup, memory selection, data transfer, and completion. Understanding these cycles helps us optimize our programs for better performance. Data alignment is crucial for efficient memory access. When data is properly aligned to word boundaries, the CPU can access it in fewer cycles. Misaligned data often requires multiple memory accesses, significantly impacting performance. Finally, we have various memory access optimization techniques. These include prefetching, caching strategies, and careful data structure design. By applying these best practices, we can dramatically improve our program's memory performance. Remember, understanding these memory operations is fundamental to writing efficient code. When you grasp how load and store instructions work, how timing affects performance, and how alignment impacts access speed, you become capable of making informed decisions about memory usage in your programs. Now that we've established the fundamentals of memory basics, Let's dive into one of the most crucial concepts in modern computing: virtual memory. Virtual memory fundamentals represents a paradigm shift in how we think about memory management. It's the foundation that enables modern operating systems to provide each process with its own isolated address space. The key distinction here is between virtual and physical addressing. When a process runs, it uses virtual addresses. These are logical addresses that the process believes are its actual memory locations. But the reality is quite different. This is where the address translation process comes in. The hardware, specifically the Memory Management Unit, or MMU, converts these virtual addresses to physical addresses in real time. It's like having a sophisticated postal system that redirects mail to the actual physical location. One of the most important benefits we get from this system is memory protection. Each process is isolated in its own virtual address space, preventing one program from accidentally or maliciously accessing another program's memory. The system benefits are tremendous. We achieve efficient memory utilization, better security through isolation, and the ability to run programs larger than physical RAM through techniques like paging and swapping. This virtual memory foundation is what makes multitasking operating systems possible. Now that we understand the fundamental principles of virtual memory, let's dive deeper into the actual implementation details. We'll explore how the operating system translates virtual addresses to physical ones through paging mechanisms. The paging mechanism is the heart of virtual memory implementation. Page tables act as lookup directories that map virtual addresses to physical memory locations. Each process maintains its own page table, allowing multiple programs to coexist without interfering with each other's memory space. However, consulting page tables for every memory access would be too slow. That's where the translation look-aside buffer, or TLB, comes in. This specialized cache stores recently used page table entries, dramatically speeding up address translation by avoiding repeated page table lookups. Sometimes, a program tries to access a page that isn't currently in physical memory. This triggers a page fault, an interrupt that tells the operating system to load the requested page from storage. The OS handles this transparently, swapping out less used pages if necessary to make room. Memory mapping takes virtual memory a step further by allowing processes to share memory regions efficiently. This enables features like shared libraries, where multiple programs can use the same code in memory, and memory-mapped files, where file contents appear directly in the process's address space. These implementation details work together seamlessly to create the illusion that each program has its own dedicated memory space. Understanding these mechanisms is crucial as we move forward to explore direct memory access and advanced memory management techniques. Building on our understanding of virtual memory implementation, we now move to one of the most powerful techniques in memory management: direct memory access, or DMA. This technology revolutionizes how our systems handle data transfers. Let's start with the DMA controller itself. The DMA controller is a specialized hardware component that manages data transfers between memory and peripheral devices without constant CPU intervention. It has its own registers to store transfer parameters like source address, destination address, and transfer count. The real power of DMA lies in CPU offloading and parallel processing. Instead of the CPU handling every byte of data transfer, the DMA controller takes over this responsibility. This means the CPU can continue executing other tasks, while data moves in the background, true parallel processing at the hardware level. DMA supports multiple transfer modes and protocols. We have burst mode for maximum throughput, cycle stealing mode for balanced operation, and transparent mode for minimal CPU impact. Each protocol serves different performance requirements and system constraints. Finally, interrupt handling and completion notification ensure the system knows when DMA operations finish. The DMA controller generates an interrupt to signal transfer completion, allowing the CPU to process results or initiate the next operation efficiently. DMA is essential for high-performance computing. From disk I/O to network transfers, it enables our systems to achieve the throughput we expect in modern applications. Next, we'll test your understanding with an advanced memory concepts quiz. Now that we've covered the theoretical foundations of memory management, it's time to see these concepts in action. Let's set up our demonstration environment where we'll explore practical memory management techniques. First, let's examine our demo environment and the essential tools we'll be using for our memory management demonstrations. We'll be working with Valgrind for memory debugging, GDB Debugger for step-by-step analysis, System Monitor for real-time observation, and various test programs to simulate different scenarios. These tools form the foundation of professional memory debugging. Next, we have our memory monitoring utilities that will help us track memory usage in real time. We'll use htop and top for process monitoring, ps command for detailed process information, /proc/meminfo for system-wide memory statistics, and pmap utility to examine memory mappings of specific processes. Performance measurement is crucial for understanding the impact of our memory management decisions. We'll measure execution time, track memory usage patterns, monitor CPU utilization, and analyze the overall system performance impact of different memory management strategies. Finally, let's look at the common scenarios we'll demonstrate. We'll explore memory leaks and how to detect them, demonstrate buffer overflows and their consequences, compare stack versus heap usage patterns, and examine various allocation strategies. These scenarios represent the most frequent memory management challenges you'll encounter in real-world programming. With our environment ready, we're prepared to dive into hands-on memory management demonstrations. Excellent work, everyone. We've now completed our comprehensive journey through memory management concepts. Let's take a moment to consolidate everything we've learned in this final summary. First, we explored the memory hierarchy, from lightning-fast cache memory at the top, through RAM for active processes, down to storage layers for persistent data. Understanding how data flows between these layers and optimizing access patterns is crucial for system performance. We then dove deep into virtual memory, that brilliant abstraction layer that gives each process its own virtual address space. This enables process isolation, memory protection, and efficient memory utilization through techniques like paging and swapping. Direct memory access optimization showed us how modern systems achieve high performance by allowing devices to transfer data directly to memory, bypassing the CPU. This offloading technique is essential for handling high-bandwidth operations efficiently. Finally, we covered best practices that you'll apply in real-world development, preventing memory leaks, writing cache-aware algorithms, and designing systems that work harmoniously with the memory subsystem. You now have a solid foundation in memory management that will serve you well in systems programming, performance optimization, and understanding how modern computers really work. Remember, memory management is both an art and a science. Keep practicing, keep experimenting, and always consider the memory implications of your design decisions. Thank you for your engagement and excellent questions throughout this course.